In this section of the worksheet, we are dealing with a slightly different measurement. In this section of the worksheet, we're dealing with the sample proportion, whereas before we were dealing with the sample mean. As a reminder, the sample proportion, for example, is the fraction of vegetarians in my 1220 class. That's a proportion, a sample proportion. So, since we have a slightly different measurement, we can still use the central limit theorem, but we have some changes to it. So, remember that to use the central limit theorem to derive the sampling distribution of our sample measurement, we need to check a few conditions. In the case of the sample proportion, our conditions are a little different than before. First, we check, do we have a random sample? Well, let me see. Does it tell us? It actually doesn't tell us if our sample is random or not, so we'll have to assume yes, since we're not told otherwise. The second condition I like to describe as, is our sample an appropriate size? So neither too large nor too small. We have two criteria that we need to check. So we need to check, is our sample size no more than 5% of our population? So in other words, that our sample isn't too big. Let's double check. So our sample is 500 people. What's our population? Well, the population that we want to know about is the US population. Well, the US population is really big. I think it's like, what, 350 million at this point? So 500 is definitely smaller than 5% of 350 million. So this is good. And then we also want to check that our sample isn't too small. So we check that the sample size times our known population proportion is greater than 5, and that our sample size times 1 minus that proportion is greater than 5. So here, and remember that n is 500, our known population proportion is 9%, or 0.09. So let's see, 500 times 0.09, let me plug that in my calculator, is 40. Oops, actually that's not true, it's 45. Which is definitely greater than 5. So that's good. Next we check 500 times 1 minus 0.09, which is 0.91. I can plug this into my calculator. Let's see. Well, this is definitely greater than 5. So to be exact, it's 455, which is very much greater than 5. So that condition is satisfied. So for your notes, let me highlight these for you. These are the conditions we need to check. Do we have a random sample? Is our sample size small enough compared to the population? But is it larger than this? So you need to make sure it's not too big, not too small. Okay, so then, because all of these conditions are true, we can use the central limit theorem. I'm going to abbreviate central limit theorem. And so we know that the sample proportion is distributed approximately normal, with the mean equal to the population proportion, which is 9%. And a standard deviation. So let's see. And a standard deviation equal to the square root of the population proportion times 1 minus the population proportion over the sample size. That's our formula for the sample standard deviation. And so we can plug it in. This is 0.09 times 0.91 over our sample size of 500 and take the square root of the whole thing. That's our sampling distribution of the sample proportion, according to the central limit theorem. So, a couple things to note that are a little different from when we're talking about the sample mean. The mean of the sampling distribution will be the population proportion, P, so that's 9%. The standard deviation of the sampling distribution is where this is different from before, where the standard deviation is given by the population proportion P times 1 minus P over the square root of n. Take the square root of the whole thing. All right. Part B, now we can apply this. We want to find the probability that the sample proportion is greater than 0.11. So we want the probability that p hat is greater than 0.11. Since we know our sample proportion is normally distributed, we can convert this to a z-score. So I just do my conversion formula. So I take 0.11 minus the mean, which we said was 0.09, divided by our standard deviation of our sampling distribution. Our standard deviation was given by this formula. If I plug this into my calculator, you should get that this equals 0.012. So I'm going to divide by 0.012. If I plug this z-score into my calculator, I should get 1.67. Remember, to find the probability that z is greater than some value, that's the same thing as finding 1 minus the probability that z is less than that value. I can look up the area to the left of 1.67 in my normal table, which should be 0.9525. 1 minus 0.9525, you can plug into your calculator. You should get 0.0475. So the probability that the sample proportion of colorblind people is greater than 0.11 is about 4.75%. Part C. What is the probability that the sample proportion differs from 0.09 by at most 0.05 units? This should really have an at most there. Okay, so what's the probability that the sample proportion p hat differs from 0.09 by at most 0.05 units? So in other words, what's the probability that the sample proportion is within 0.05 of the population proportion? So in other words, it can be 0.05 more than the population proportion, or 0.05 less. maybe for clarity I'll say within 0.05 units of 0.09. So in other words, what's the probability that the sample proportion is between 0.09 plus 0.05, which is 0.14, and 0.09 minus 0.05, which is 0.04. To find this probability, since I know the sample proportion is normally distributed, I convert to z-scores. So I take 0.04 minus the mean. As a reminder, let me rewrite the distribution of the sample proportion. 0.04 minus the mean of 0.09 divided by the standard deviation. I do the same thing with 0.14. Divide by the standard deviation. If I plug this into my calculator for my two z-scores on either side, I should get negative 4.167 and positive 4.167. To find the area between two z-scores, I take the area to the left of the larger one, subtract the area to the left of the smaller one. This is a really large z-score, so I can approximate the area to the left with 1. This is a really small z-score, so I can approximate the area to the left with 0. So therefore, there's a 100% chance that the sample proportion of colorblind people is within 0.05 units of 0.09, the population proportion. Now, let's suppose that the sample proportion was 0.12. Is this unusual, and what conclusion can we draw about the population proportion? So, as a reminder, our sample was 500 people, and we suppose now that our sample proportion was 0.12. And as a reminder, the population proportion was 0.09. The hat on P here, the hat denotes that we're talking about the sample proportion. If there is no hat, then we're talking about the population proportion. Okay, so to figure out if a value is unusual, let's look at the probability of seeing a value as or more extreme than our population proportion. So we can look at what is the probability of observing a sample proportion greater than or equal to 0.12. In other words, what's the p-value? So recall that by the central limit theorem, we know that the sample proportion is distributed normally with mean equal to the population proportion and standard deviation equal to p times 1 minus p over square root of n. Oops, actually, whole thing square rooted, which we said was 0.012. So we can convert this to a z-score. 0.12 minus 0.09 divided by 0.012. If I plug this into my calculator, this z-score should be approximately 2.5. I can calculate the area to the right of 2.5. That's 1 minus the area to the left. The area to the left I get from my z-table is 0.9938. So the area to the right is 1 minus that, which is 0.0062. This is less than 0.05, remember that if our p-value is less than 0.05, then we know that we're dealing with something very unusual. So our sample proportion is unusual. This, gives us evidence that the population proportion may not be 0.09, because if the population proportion was 0.09, the probability of observing a sample proportion as or more extreme than 0.12 was very small. So the population proportion is probably not 0.09 if we can observe a very unusual sample proportion. So that's how we conclude that the sample proportion is unusual using the p-value approach. Another way that's perhaps a little simpler is simply to look at the z-score. Remember that our z-score represents how many standard deviations away from the mean, from the center of the distribution are we. So if our sample proportion is more than 2 standard deviations away from the mean, then it is an unusual value. This comes from our empirical rule, because the empirical rule says that for a normal distribution, for a bell-shaped curve, 95% of observations are within 2 standard deviations of the mean. So if our sample proportion is more than 2 standard deviations away from the mean, that means that it's in that 5% that's outside of those 2 standard deviations. It's part of just 5% of the distribution, rather like we're talking about our p-value. So if our sample proportion is more than 2 standard deviations away from the mean, then it's an unusual value. And our z-score is exactly how many standard deviations away from the mean an observation is. So if we convert our sample proportion of 0.12 to a z-score, well, we do that by taking 0.12 minus the mean of our sampling distribution divided by the standard deviation, because we know that this is normally distributed. This will be 2.5. So 0.12, our sample proportion is 2.5 standard deviations away from the mean. 2.5 is more than 2. So our sample proportion is unusual, which leads us to believe that the population proportion is probably not 0.09.